everyone, here we are wrapping up week 2 of this course with our final video. Today's discussion revolves around additives used to fine-tune material properties, particularly focusing on the fresh characteristics, because we've been actually looking into the fresh properties of materials, and it is also crucial for printing processes. Plasticizer or superplasticizer is the most common chemical additive to control materials' flowing behavior. Among them, the widely employed types are polycarboxylate or PCE-based superplasticizers due to their exceptional effectiveness. The PCE has a sophisticated molecular design that enables them to effectively disperse cement particles in cement mixes. These PCE molecules are crafted with a curve-like arrangement, feature lengthy main chains alongside flexible side chains containing carboxylic acid curves. These pliable side chains attach themselves to cement particle surfaces through adsorption. Once adsorbed, these PCE molecule side chains create a protective shield around the cement grains, inhibiting close contact between the particles. Therefore, the initiating a repulsive force is known as a steric hindrance. Consequently, the particles disperse effectively, pushed away from each other, significantly enhancing the concrete mix's fluidity and workability. The adsorption of PCE molecules onto cement particles reduces particle attraction, thereby minimizing the water demand required to maintain workability. This reduction in water demand is very important, pivotal for achieving heightened or increase the concrete strength, high performance concrete, and durability while preserving flowability. Given that printable materials are engineered with a low water to cement ratio and then high fine content, the addition of superplasticizer aids or helps in achieving optimal flowability with minimal quantities. However, precise control while using plasticizer is essential, as its impact on flowability can change drastically at certain thresholds. Another category of chemical additives is the viscosity modifying agent, or we can normally call it VMA, serves to regulate and fine-tune concrete's rheological properties, particularly viscosity and flow behavior. VMAs utilizes various base materials such as a cellulose, starch, or fiber, each with distinct traits. Their incorporation enhances adhesion and stability, better pumpability, reduces viscosity through hydration control and polymer interaction, mitigates friction, and manage thixotropy, and so on. The next chemical additive we can actually visit is the setting control chemical additives like accelerator or retarder. Let's revisit the concept of buildability. In the printing process, factors like yield stress and its evolution, the strength of evolution, as well as printing parameters such as pass time, printing speed, play pivotal roles. Imagine constructing a house within a tight project deadline. It might be necessary to increase the printing speed. However, it's crucial, or you need to make sure that all concrete layers can withstand the weight they will bear. In the short span, you need the greater yield stress or the greater yield stress evolution, essentially a high strength evolution rate. So this can be achieved with an accelerator. Accelerators are engineered to expedite concrete setting and early strength gain, with examples like calcium chloride, calcium nitrate, sodium nitrate, calcium formate, or triethanolamine. In practical scenarios, accelerators find use in speeding up concrete hardening, such as in urgent repair work or hastening production in precast concrete plants or early formwork removal. In cold environments where hydration rates are slowed, accelerators aid in the concrete casting process. For 3D concrete printing application, accelerators are crucial for ramping up the structuration rate in lower printed filaments to support overlapping filaments. Depending on construction speed and size, accelerators can be added during on-site mixing or directly into the printing nozzles, similar to shotcrete. Without accelerators, construction pace might need to be reduced, particularly in smaller projects like houses and precast components. This would result in short intervals between printed filaments, adjusting the construction speed to match the concrete structuration rate. For instance, like calcium chloride, which is the widely used accelerator, there is a general consensus that its ability to enhance early strength is due to its reaction with the C3A and C4AF. So this reaction creates achieved sites that favor the nucleation growth of CSH, one of the main hydration product, and facilitates the formation of ettringite or Friedel salts. Additionally, it catalyzes the coagulation of hydrosilicates, which is accountable for the acceleration process. Moreover, it lowers the pH of the pore solution and boosts the dissolution rate of hydrated lye. Conversely, in other words, so when a longer pause time is necessary, requiring the material not to stiffen too quickly, retarders comes into play to manage the setting time. These include organic retarders like sugars or sucrose and lignosulfonates, along with the inorganic options such as borates. For instance, sucrose or sugar impedes the cement hydration by forming complexes with calcium ions. Given the susceptibility of 3D printable concrete material to shrinkage, particularly due to its high fine content, absence of coarse aggregate, and increased exposure to the environment, employing a shrinkage reducing agent becomes pertinent for the performance and the long-term durability in its hardened state. Shrinkage reducing agent, or we call it SRA, function by inducing an expansion in the concrete that counteracts a volume contraction caused by normal drying shrinkage. These concrete mixtures typically include compounds like polyoxyalkyl alkyl ether, incorporating such a mixture during concrete batching, resulting in the notable reduction of the drying shrinkage about 30 to 50% in both early and prolonged drying shrinkage. Another noteworthy additive to consider is adhesion agent, acting akin to a form of glue. So given the upcoming emphasis on interlayer bond strength, which we'll talk about later, the application of an adhesion agent becomes significant. It involves applying the agent on the substrate or the lower layer before depositing the upper layer. So this facilitates a physical bond between the layers through the adhesion action, a factor that will delve deeper into the next week. After we're talking about the chemical additives, now we are moving on to the mineral additives. The mineral additives serve a primary role in enhancing long-term performance attributes such as strength, durability, and environmental sustainability, rather than directly influencing fresh concrete properties like workability. They do, but not as much as the chemical additives. Take, for instance, ground granulated blast furnace slag. We sometimes call it just like normal slag, because this is the most common type of slag, or we call it GGBFS. It's a residue from iron production that is incorporated to decrease permeability and bolster the durability in concrete. Fly ash, derived from the combustion of pulverized coal plant, is another valuable mineral additive. It has a very spherical particle shape, and its particle shape significantly enhances concrete workability, so basically helping or improving its flowability of the concrete. And also additionally, it reduces the heat of hydration and augmenting long-term strength and the durability. Both GGBFS and fly ash exhibit a secondary hydration reaction, or known as a pozzolanic reaction, where they interact with calcium hydroxide from cement hydration to form compound like calcium silicate hydrate, or we call it CSH, and other hydrate materials. This process refines the pore structure, contributing to improved strength and durability. Silica fume is frequently utilized in 3D printed concrete mixes or for the normal high performance, ultra high performance concrete, as it boosts initial strength and flexural strength post curing. The very fine and the small size of the particle fills the void spaces around larger particles, fostering stronger bonding with the cement binder. This optimization of particle size distribution enhances yield stress and buildability as well. While additional minerals additives such as a clay, metakaolin, or limestone filler, among others, exist, I will refrain from delving into the comprehensive details as our focus this week revolves around the material's fresh properties. All right. Thank you for joining and being here throughout. We've delved into various material types and their fresh properties. Today, our focus was on adjusting these properties by incorporating additives. I trust this exploration offered you a clear insight into the nature of 3D printable concrete materials. Join me next week for another 3 more videos where we'll explore the pumping techniques and material mixings. Alright then, so take care and see you soon.